Okay. Today we're going to talk about Laplace transformations. Okay, so let's first talk about differential equations in general. Differential equations are hard to solve because differentiation is a somewhat difficult concept, and its reverse, integration, is a much more difficult concept. It doesn't follow the rules we're used to following. The product rule isn't what we would want it to be. The quotient rule isn't what it would want it to be. And these are the things that make solving differential equations hard. It would be nice if there was a magical place where differentiation was simple. That would be wonderful. And that place exists. It's called the Laplace transform space. So let me first define what a Laplace transform, but first I want to start with a caveat that all functions y of t in this video are eventually less than an exponential function for some positive m. So pretty much any function that you've normally run into is going to be okay with this. But this is just a caveat I want to state up front in order to be totally mathematically honest. Okay, if we have such a function y, here's what the Laplace transform is. The Laplace transform of the function y of t is a function in a new variable s. So there's a little bit of an abuse of notation going on here because we don't have s over here. But we're just going to have to tolerate that. How do we find the function y of s? We take an integral from 0 to infinity of y of t times e to the minus st dt. So we integrate out the t out of that, and what we'll be left with is a function of s. Let's look at this expression for a moment. This is very difficult to get our heads around, especially since we're not doing one integral, but we're doing kind of infinitely many integrals, right? Because we're just doing this for a general s. So it's probably pretty intimidating, but I'll show you that it's not so bad. What is this thing doing? Well, basically, what it's doing is it's detecting how much the function y is like the function e to the st. This is a quantitative way of showing is y similar to e to the st. That's what it's asking. Okay, so let's get down to the main property of Laplace transforms that make them worthwhile in solving differential equations. And I will call this the derivative rule for the Laplace transform space. So this is the rule. Given a y of t, a function y, and its derivative, we have the following property. If we look at the derivative of y and say, decide to take its Laplace transform, what we get is s times the Laplace transform of the original y minus the original value of the function y at 0. And you can prove this by a simple integration by parts argument. I'm not going to go into that at this point. But what this is saying, right, is differentiation in the Laplace transform world is simply multiplication, which, as we know, is a much simpler operation. We learn multiplication in 3rd grade. We learn differentiation in 12th or 13th grade. So this is going to allow us to do some interesting things. And there's another property of the Laplace transform that's important as well, the linearity property. And it says that the Laplace transform of a sum of two different functions is just the separate sum of the Laplace transforms and the Laplace transform of a constant multiple of a function. F is a function, C is a constant multiple here, is just the constant multiple times the Laplace transform of the original function. So that is the linearity property. So we're going to use these properties a few times in the future. But one more thing I want to say before we start to go on here. It's important to know some common transforms. And any book that covers the Laplace transform will have a nice table that shows you the Laplace transform of some common functions. I'm going to highlight a few here just to give you a sampling of it. This is by no means exhaustive, but as I said, your textbook or the internet will easily give you nice tables of Laplace transforms. So the first one, the Laplace transform of an exponential function, is the following function. It's 1 over s minus a. So the Laplace transform of e to the at is 1 over s minus a, and that's for positive a, and the Laplace transform is an undefined function for s minus a. So the domain of the Laplace transform of e to the at is just s's which are larger than a. Okay, that's just something to keep in mind. Here's another one. The Laplace transform of a variable raised to an integer power, right? This is a common function we see. It is n factorial over s to the n plus 1. So there we go. And this is a function which is defined only for positive s. Okay, so the Laplace transform of a polynomial is easy to compute. And the last one here, another common function we've seen several times, the sine of omega t is going to be omega over s squared plus omega squared. And that's valid for all s. So those are some common transforms. Like I said, any table is going to have a dozen or more of these, and these will be included in that. But now what we want to get to, the real exciting thing to do here is we are going to solve a problem using the Laplace transform, right? At this point, you see what a Laplace transform is. You're probably somewhat confused as to what it means, but there's still no point for it because we haven't seen how it works. So let's solve a differential equation using the Laplace transform. So I'm going to do dy over dt is equal to y minus 4e to the negative t. And I'm going to put this initial condition that at time 0, y is equal to 1. Now, this is a linear first order differential equation. We could solve this with integration factors, like you've no doubt probably learned about by now. But let's solve it with Laplace transforms. So step 1 is going to be take the Laplace transform of the equation. So I'm going to take the Laplace transform of the whole equation. So the left-hand side, I'll have the Laplace transform of dy over dt The right-hand side, by linearity, this is separately the Laplace transform of y minus the Laplace transform of 4e to the negative t. All right, so what do we have here? Now, by the property of differentiation under the Laplace transform, we know what this is. This is s times the Laplace transform of y minus y at 0, right? This is what we had on the previous, or 2 slides ago, by integration by parts. Over here, well, we don't know what y is, so we'll just leave it as the Laplace transform of y. And then we use linearity to get the Laplace transform of 4e to the negative t. We know that we can pull the 4 out, and then e to the negative t is going to be 1 over s minus a negative 1, which is s plus 1. Right? So we use the fact that e to the alpha t goes to 1 over s minus alpha. Okay, so now what do? Now we get all the... So we've started this. Now we isolate L of y. We isolate the Laplace transform of y. Okay, so I get everything with the Laplace transform of y on one side. So that's going to be s times the Laplace transform of y minus Laplace transform of y. I move the y at 0 to the other side, but recall that's equal to 1. So that is going to be 1 minus 4 over s plus 1. Okay, now I need to do some factoring. Let's start a new slide here. So this is going to be s minus 1 times the Laplace transform of y is equal to 1 minus 4 over s plus 1. Now we isolate L of y by dividing both sides by s minus 1. Okay, so now we've isolated the Laplace transform of y. And then the final step is to untransform. And this is perhaps the hardest step. Okay, recall that the Laplace transform of e to the at is equal to 1 over s minus a. So we could untransform this part fairly easily, but this part we don't actually have on our table, right? So what we need to do is we need to do a partial fraction decomposition here. So 4 over s plus 1 times s minus 1 is equal to some a over s minus 1 plus some b over s plus 1. And when you solve that using the techniques you've learned before, we have 2 over s minus 1 minus 2 over s plus 1. So going back to our equation, we have the Laplace transform of y is equal to 1 over s minus 1 plus, we got a minus sign here. So that would be minus 2 over s minus 1 plus 2 over s plus 1. So altogether we have a minus 1 over s minus 1 plus 2 over s plus 1. And now we undo the Laplace transform, right? E to the t becomes 1 over s minus 1. So we have a negative e to the t. Well, I shouldn't use an equal sign right here. We're done with the Laplace transform part. Now I'm ready to untransform. First term is negative e to the t because 1 over s minus 1 is the Laplace transform of e to the t. And the negative sign happens because of the linearity property. And then we'll have 2 of whatever function's Laplace transform is 1 over s plus 1. Well, looking at this up here, that is e to the minus t. And we have solved the differential equation. You could differentiate and check that this is indeed the solution. Right? So working in the Laplace transform space can sometimes allow us to unwind the difficult differentiations and integrations that we'd have to do and just turn them into simple algebraic operations, like figuring out this partial fraction decomposition.